Everyone,
Yes, no, we
moment of silence for WPA2. So I'm going to go a little bit into ROP, which is an exploitation technique if you're trying to like exploit a program. I've got a little bit of background in here so that this applies to more people, hopefully. So hopefully you'll get something out of it. So should I go ahead and start presenting? All right, so a little bit of background to start with. You've got the exploitation method, which is a stack-based buffer overflow. So the idea is you have, the idea with a stack-based buffer overflow is you've got some memory on the stack, like you could have like a string in there. So you're trying to read in a string from the user. But you kind of screw up when you're programming that and you copy more memory than you can fit into the space. And you basically go past where you're supposed to write and cause some fun stuff. So a little bit of background knowledge. If you've taken like computer science 1 or 2, you should know like what a stack is. It's a data structure where you can put something on the top or pop something off the top. So it's a first in, last out data structure. So the first thing you put in, last thing you take out. So the stack traditionally grows down from higher memory addresses to lower memory addresses. So when you're putting something on the stack, you actually lower the memory address where you put that. And then typically when you're using a program, you'll make a function, and so each function call will have its own stack frame. And in that stack frame, you've got that data for that function. So local variables for the function are put at the top of the stack frame, and then you have a couple of extra values at the bottom that are important for program flow. So I'm not going to be the most amazing at explaining this to people who aren't too familiar with assembly, but I'll try. So pretty much, depending on the calling convention you use, which is how your processor actually calls a function, you might put some arguments on the stack for your function, and then you will run a call instruction on your processor. So like you would have like in C or in Java, you have like public stack void main, and then it takes in a string array of arguments. So string array args would be the argument that you'd push, and then when you call into main, you put the address that you want to return to on there, and then there's a stack pointer and base pointer. So on Intel, those are called RSP and RBP. I'm so sorry. I feel, again, this is hastily prepared. So your stack pointer is at the top of the stack frame. Base pointer is like at the bottom of where your variables are, and then you have that extra data. So the idea is to exploit this, you can actually, if your buffer is in local variables, you can start reading into that and read past it. And what you can do is you can actually overwrite the return address. And when you overwrite the return address, you can make it execute whatever code you want from anywhere in memory. So an example of a program that will be vulnerable to this is right here. So you make a buffer on the stack for a name variable, which is just 32 characters long. And then you're just going to say, hey, what's your name? And you're going to use a function called getString, getS, which is terribly, terribly unsafe, because getS does no checks on how big the string is you're reading. So it will keep on reading data from the user until it encounters a new line character. And what's going to happen is if you put in more than 32 characters into the name field, it will actually go through the saved base pointer and through the return address, and if you corrupt that, you can execute whatever you want. So what the traditional method of attack for this would be to write some, what they call shellcode, into the name variable. And so that's just a small bit of assembly code that typically doesn't have like a null byte, or there might be some characters that are excluded from what you can use depending on how the function works. So gets, as long as you don't put a new line in there, it's fine. And that's some code that you want to execute. And then you overwrite through there. And then for the return address, you just put the address of where name is in memory. And so you put your code in where the name is, and then you end up causing it, when the function returns, it will jump to that code and run it. So there are some mitigations on modern systems typically. The simplest one is what's called a stack cookie. So what a lot of modern systems do is between the local variables and the data here, it will actually insert an extra value that gets saved there at the beginning of the function being called, and then it gets checked before it returns. So it calls another function to check it. And if that value got changed, if it doesn't match, then your program will just exit without doing anything else. So you would have to overwrite through it to get to the return address, and because you check to make sure it hasn't been ridden through, it's very difficult to actually get code execution reliably that way. There's also ASLR, which is address space layout randomization. And so the idea with that is, with your code, traditionally everything is loaded to a specific place in memory. So you know exactly where everything is. You'll know where that name variable is when the program runs. But with ASLR, the idea is when you load the program into memory, you randomize where the addresses are. So usually you would take like the code for the program and like shift it by a certain value. But often that value, it can be shifted by so many different positions that it's very hard to reliably predict where that is. And if you don't know where name is, you don't know what to overwrite the return address with, and so you'll just jump somewhere randomly and probably not get the effect you want to have. And then the last one, which is what we'll be focusing on in this talk, is something called no execute, also known as data execution prevention, or DEP, or write XOR execute. The idea is you actually can set permissions on the memory management unit of your computer to say that this data can be executed or this data can be written, and you just make sure that there's no overlap. So if you're loading code into memory, you mark it as executable but not writable, so that you can't overwrite code in memory. And then when you've got data in memory, you mark it as writable but not executable. So you can't just put code in memory and jump to it and expect it to work. Of course, there are some countermeasures. So with stack cookies, you got a couple options. You can use another vulnerability in the program to actually leak that. So if you can find a way to print out the stack cookie to the user or get it out to the user somehow, you can use that and mutate the payload that you're going to send the program so that you can actually use that leaked value in place of the stack cookie. And then you just write through, you overwrite the stack cookie with the same thing, write the return address, and there you go. You could also do something else. So some programs, you might be able to change program flow. In the local variables, you might have like the buffer at the top, and then you'll get like an integer value maybe below it that you can write into that does something interesting if you incorrupt it. So you can write through to that integer and then change how it flows that way. You might not even need to overwrite the return address to do something you want to. You can also, go past stack-based exploits and look at the heap. And there's some fun stuff you can do there I can tell you about if you want after this. ASLR, a couple options. Sometimes you can brute force it. Typically on 64-bit systems, this is not going to happen. It's not reasonable. But on a 32-bit system, if you can run a program quickly, and if you can run a program a lot of times really fast, sometimes there's only so many bits of the address that can be randomized. And so you can basically just assume it's one address and keep trying till it works. You can also, again, like with defeating stack cookies, you can leak a memory address, and if you know what that value is, you can calculate an offset to something you want to work with. Or you can just, in your code, you can use relative offsets. If you can get code execution, then your code can just have relative jumps and relative calls. Instead of saying it's at this address, say it's like 20 bytes from the current address. And then NX. Just use existing code in memory. Your program's got some code in there, so let's just take advantage of that. And that's how we get into ROP. So the theory kind of, you can return, usually you've got that return address returned to a function normally. If you put in some code, you can return to that, but you don't have to return to anything that's like a function of any kind. You can return, say, near the end of a function. So something that's pretty common is you search for what are called RapGadgets, and you can actually look for small pieces of code next to return statements, and when you're overflowing the return address on the stack, keep on going and overflow a bunch of return addresses that might happen. So you will jump to code here and then return, and then that return will jump to code at the next address that you put on the stack. And it just cascades through and runs all of those instructions. And there are tools to look for those. So here's an example here. Couple of technical details, but on Linux, 64-bit, you basically put, if you've ever looked at assembly, you put your arguments to your function calls in order in those registers, which are little temporary workspaces in the processor, and then you can call the function. So an example of calling a function with 2 parameters using ROP, you can find a gadget that does pop RDI and then ret. And so that'll pop that off the stack when you run it. And then the next one, it'll pop that off and put it into the RDI register. You can do the same for RSI. And then once you've done that, you've got the function parameters loaded in, and you can just call the function. And there you go. Instead of doing this yourself using your own code you've put into the program, you can just take advantage of this existing code in the program, which is already marked executable for you, and run it. Note that if you have ASLR, you obviously have to do stuff to, or if you have ASLR or stack cookies, still need other stuff to defeat those, but this will defeat NX. So basic idea is, with a big enough program, you can basically get Turing completeness. You can write any program you want with RapGadgets. Of course, this is painful and awful, so it's very common to write some code that will mark another area of memory that you can control as both writable and executable. And so on Windows, you might try to make a call to this virtual protect EX function, which changes the permissions on the memory, or on Linux, basically the equivalent would be mprotect. And so you can actually change permissions on memory once it's running, and make it so the code that you've injected elsewhere can be run and then jump to that. And so you can still do more traditional programming once you get through the ROP stage. The other good thing is on x86, which is the architecture you've got on your Intel processors in most of your computers, it's a variable length instruction set, which means the instructions get encoded as a sequence of bytes. The number of bytes you have varies for what an instruction is. And so it's often possible, if you have an instruction that like moves data from this location to this location, let's say that's a 4-byte instruction. If you just jump like 1 byte into that, you might actually get a completely different but still valid instruction. So you can even use code that's not explicitly in the program for your ROP. And then one other thing. Sometimes you might not have control of the stack directly. Maybe you need to avoid screwing with a stack cookie or something. If you can execute one gadget, then you can try to get what's called a stack pivot. And so a stack pivot is when you find a ROP gadget that will actually put something in the stack pointer, put a pointer to memory you can control in the stack pointer. And so what you would do is you would put something in a buffer, doesn't even need to overflow it, and then you can actually just find a gadget that will, make that the new stack. And from there, you can pop off values in return like you normally would with ROP. So I know that was very dense, probably. I will happily answer questions, either right now or at the end. If you really don't understand something, I can explain it now. Are there any quick questions before I do a quick demo of that?
So when you have something on the call stack, so if I was going to use something like proc explorer and actually look at like stack threads being ran, would I be able to see what memory addresses they were coming from at that point? So the thing about ASLR, I don't understand. At what point is it obfuscating where that memory address is? I mean, can we look at the MMU and get it to?
So ASLR is usually applied by the program loader. So when your program is loaded into memory, it is at that point that it will determine where it's going to be running. after it's loaded in memory, it's at a fixed address until unless that program like crashes or closes for some other reason and restarts. So once you know an address in a running program, you can figure everything else out from there. All right. Anything else? All right. So I've gone ahead and I have pulled a couple of exercises from this website I found, which actually looks pretty good. So this is just a website with some basic introductory ROP exercises. And so I have pulled these down and I've got them on my machine here. So the first one that they've got is called, RetToWin. So RetToWin is their first one. They've got both a 32-bit version and a 64-bit version. I'll just be doing the 64-bit one. So I'm going to go ahead and just to check that they're doing things right, I'm going to use a nice little tool I like here, Radare, which is a reverse engineering framework. And it comes with a tool called RABin2, so you can look at the properties of the file you're trying to examine. So if you look at it, it has no execute marked as true, meaning this binary, when it's loaded, will mark data sections as not executable. So we will have to use ROP to go ahead and figure this one out. So I'm going to go ahead and load this up into Radare, do a little bit of analysis, and then I'm going to go ahead and take a look at the main function. So I'm doing here, all those A's does some auto analysis. S seeks to the main function, so you'll notice this address it's at in memory, and then it went over to where main is, and then this stands for print disassembly of function. So we're going to pull up some assembly here for what the main function does. So if you just kind of keep a high-level overview, it does something. Sets some properties of a buffer, makes a buffer. I don't know. I don't really care. Loads in a string into DI, which is the first argument on 64-bit Linux. And it loads in this string that says RetToWin by ROP Emporium. Just puts the string on the screen. So it prints it out. 64 bits, prints that string, and then it calls a function called pwnme. Sounds kind of interesting. So we're going to take a look at that function if I can type. And so that function, prints some stuff out to you. And then it calls fgets. So fgets is a little bit safer than gets. You can still screw it up. So fgets takes a character array, which is that's the pointer to the string that it's going to populate. So that's the pointer to the buffer it's going to put your string in. The number of characters it's allowed to put in there, and then a pointer to the stream that it's going to load from. So this will actually load it from standard input, which is just when you're typing into the console. So the thing they're doing here, though, is they allocate 20 bytes of memory for the string to go into, or a hex 20, which is 32 bytes. Down here, they try to read 50 bytes of data into that. So we're going to be able to do a traditional stack-based buffer overflow. You'll notice before it returns, there's no stack cookie that's being checked. It will just happily go through. So, well, that feels pretty good so far. So we've got a nice little thing we can overwrite. Now, it does actually tell you about this on the page. There's another function in here that's called RetToWin. And so if we look at that function, all that function does is it calls system and prints out a flag. So this just runs a shell command. And so this is our goal. We want to run this function. So how are we going to do that? Well, we're going to take note of the address of this function here. We're just going to copy that a little bit. And then we're going to go ahead and start taking a look at what we can do with the program. So I can actually use Python here. I'll use Python too because a lot of people like that, and it is honestly nicer largely for printing out raw binary data. So in theory, I'm going to need 32 characters of something to fill up that buffer. It's a 32-byte buffer. After that, if we look at the image, if we look at the, if we look at what we're overflowing through, so the local variables, that's just the buffer in this case. We're also going to flow through a save base pointer. And so that is 8 bytes long on 64-bit computers. And then we can get into where our return addresses would normally be. So we're going to go ahead and make that 40 to flow through both the buffer and the saved EBP. And then we are going to make the return address that pointer there, where that function is in memory. So we're going to actually take this and put that where our return address would go. And just really quickly to show you guys kind of how this will crash. What did I mess up? Yep, thank you. It's trying to run a Python script file called that. I really am. So you'll note that crashes, and if I believe, yeah, if we pull up the system log, we can actually see segmentation fault, meaning it tried to access memory it shouldn't, at address 343333231, which is 4321 in ASCII. So we know that we're crashing it. That's great. So that is where it's trying to return. So let's go ahead and put in the actual value we want.
Is it 4321 because of
Yep. Yeah. So I lost it. It's going to take a while to get back to that, isn't it?
Oh.
All right. I just did dmessage. All right. So 408.11. So something that you need to know about Intel processors and a lot of this low-level stuff in general is Endianness. So the address is 400811 hex. Now in the processor, it stores the bytes for the address in reverse order. So when I'm putting the raw bytes in here, I have to do the last byte is 11. The second to last byte is 08, and then 40. And so I need to put all that in. And then it's a 64-bit machine, so the pointer to the function is going to be 8 bytes long. So I just need to pad this out to zeros. And so what this is going to do is it's going to put 40 bytes of garbage in the exploit file, and then put a return address to 400811. And if we go ahead and give that as input to the RetToWin file, it prints out the flag. So we successfully called into that function there. It crashes because we're corrupt. You could actually try to make that cleaner. You could. I'm not bothering. So, yeah. All right, so that's their easy mode. All you have to do is put a return address to a function to solve that one. Their second challenge is called split. And so this one, you have to actually have multiple RapGadgets used to solve this. So I'm going to go ahead and look at this one just like I looked at the other one. So it looks mostly the same. It's still calling that pwnme function. So let's take a look at what that does. Basically the same, just different stuff gets printed out. So we have to figure out how to get this to call some code we want. So they've left us a couple of little hints here. They've got this function that is literally called useful function. So we're going to look at what useful function does. Useful function loads in /bin/ls into the first argument and then calls system. So this just calls bin/ls, so it just lists the files in the directory you're in. That's not useful. Now, on the website, they also give us a hint saying, the string's still in there to cat out the flag. So I am going to use, as Radari, this is info 0 terminated strings. And then tilde is an internal grep. So if you've used Linux, grep is a tool that searches for a string in the output. And then we're going grep for just bin, why not? And so we see two strings that have bin in them. This one, bin ls, which is the one we're loading here. And then we've also got bin cat flag.text, and that is at this address. So I'm going to go ahead and make note of that. We're just going to open up Vim here, which does not want to scale. That's sad. And we're just going to put, I probably want to know that address, 601060. I'm so sorry that it's not scaling. All right, so that's probably a good thing to know. Something else we might want to know is, well, we're going to want to call system at some point. So we can just go to this call. That would honestly work, but why not just figure out where sim.imp.system is, which is just the imported system function. So we're just going to look at our function list, and system is at 4005EO. I did not. I'm also not focused in that window is the issue. All right, so our system call is at 405EO. Now, yeah, so the linker is what's responsible for loading your program and providing it with the libraries that it wants to use. So the linker, there's actually a spot in the program where the linker will put a pointer to the address for the system function. So it loads in your program, loads in the C standard library, and then updates a part of your program to point to the actual where the system function is in memory. So that's going to be where it imports it in your program, and then that will then call the actual version. So now that we've got that, we're going to actually use a nice tool called RapGadget. And so this is going to give you a little bit of fun output here. This tool will print out a bunch of RapGadgets, surprisingly, in the file you give it. So if I just run this natively,
Is that part of Radari?
No, this is actually a separate tool. Radari does actually have some ability to find RapGadgets. I just prefer this tool personally. So this prints out a bunch of stuff. So these are all sorts of RapGadgets that found in the code. So these are assembly instructions that are followed by a return. And so we've got some cool stuff here. But if we think about so we're looking for something that's useful to us. And what we've got is we've got the address of a string in memory, and we've got a way of calling a function that could, in theory, execute that string. The first argument is RDI. So what if we could find a RapGadget that could put something in RDI for us? So I'm going to go ahead and say R or E, just in case, SP or DI. RDI is the 64-bit version, EDI is the 32-bit version. Either would have the exact same effect. And so we find a RapGadget here, which literally does pop RDI, which takes a value off the top of the stack and puts into the RDI register and then returns. So we now have everything we need to build a basic rap chain. So that gadget is at 400,883. So now that we've got all of our addresses we need, we can build an exploit. So I'm going to do this a little bit more nicely for you guys here. All right, so we're going to make a Python. Instead of trying to do that all on the command line, this might be a little bit more readable. So I'm going to import a Python library called struct, which makes it really easy to work with raw binary data. And then what I'm going to do is I'm just going to make, here's some bytes, just an empty byte string. And we're just going to append to that whatever we want. So let's say that we want to have, just like before, this binary needs 40 characters to get down to where the return addresses are. So we're going to put 40 junk characters, we chose A, into that string. We're also going to need some addresses. So what I can do is I can do exploit add And then we can use the struct library to make this far nicer. So I can do struct.pack, and this will take a string. Oh boy, which one is big endian? Little endian. I think it defaults to platform, but
I think it defaults to correct.
Yeah.
So if you just put like
I'm just going to try this. Yeah.
YOLO.
So this is either big endian or little endian. One of either less than or greater than should give us what we want, and that will basically flip the byte order for us. And then the Q means a Q word, which is basically 8 bytes of data. So this will pack an integer that's 8 bytes long into just raw binary data for us. So we can just put in the addresses normally. So let's see, this is our string here. This is our call to system. And then the last one is the pop RDI gadget. So first thing we want to use is the pop RDI gadget, which is at 400.883. Yeah. So we'll put that into our exploit. That'll be the first return address we hit. Now that address is going to call pop RDI, which is actually going to take another value off the stack and put into RDI. So this one's not going to be a return address. This one's going to be our string, which is at 601.060. And then lastly, once we have that in, we can go ahead and we can call system, which is 400.5EO. And then we're just going to, admittedly Python 3 is a bit of a pain with this, with praying raw byte system to standard output, but bear with me as I write this awful thing. All right, and we're just going to write our exploit to standard output. So if we run genexploit.py, we get that, and if we look at that at a hex dump, you can see that we're printing out, here's 400.883, 601.060, 400.5EO. So we've got our return addresses in there. So now all we have to do is run the exploit. Should probably do that. I am very bad at typing when my head is at this bad of an angle. And we get to print out our normal output. Just show you that it doesn't just do that. You know, you just type random stuff. It doesn't do that. So we have successfully exploited with a basic ROP chain.
So the first thing executes goes to code that pops that string onto the
Correct.
And then that string is the argument to the function.
Yeah. So the first thing you do is you return to a gadget that does pop RDI and then returns. And so that will take the next thing off, which is your string value, and then puts into RDI. And then you call system with the string in RDI, and it works just like you'd normally expect it to. All right. Any questions?
Sorry, system parameters not passed on the stack.
So that's an interesting thing.
Can you repeat the question?
Yeah, I was thinking about that. So the question for anyone who might end up watching this video, are system parameters not passed on the stack? So if you actually look at their 32-bit versions of these, the calling convention changed. Give me a second to actually get that right. So if I actually look at this one in Radare, and I seek to, I'm assuming there's still useful function. Oh, analyze. So on here, you actually you'll note that it's pushing the address of the string on the stack before it calls. That is a difference in calling convention between 32-bit and 64-bit Linux. If I pull up x86 calling conventions on Wikipedia here, you can get some good information. I've actually linked this somewhere in the presentation. And so it gives you some details about that. But on Itanium 32 is x86. depending on the compiler you've got, it uses different conventions. GCC, which is what basically determines how everything on Linux works, it just pushes stuff on the stack in reverse order. So the rightmost argument in your function, in your function signature, is the first thing it pushes, and that pushes from right to left. With 64-bit, stack corruption is not a fun thing, so they decided that the primary calling convention will actually try to put arguments into registers first and only put stuff on the stack if it runs out of room, if it doesn't have enough registers to pass all the data. So the 64-bit binaries pass it in the registers, 32-bit will pass it on the stack. And that's an interesting detail you have to know. And then Windows has its own calling convention too. 64-bit Windows uses a completely different set of registers for calling, or, well, completely different order. Any other questions? I will try to answer anything that I can.
Could you pull up that RapGadget thing that you were using?
Yeah.
So GitHub, right?
Yes, it is on GitHub. You can also actually, if you want to, install it through pip.
Okay, cool.
So it's already installed, obviously, but that will actually pull down RapGadget, install Capstone as a dependency, and there you go. You have RapGadget now. There are some other tools. One that's a little bit more nicely interactive is called Wrapper. But here's the fun thing about Wrapper, is it colors all the output. And so there's a convention with most command line programs where if it's running interactively, meaning it's printing out stuff to a user, color is fine, that's nice. If you're piping it to a program, color is bad. So observe what happens when I grep for pop RDI. Nothing. I know that gadget's there. Just RDI?
What about
I swear that put something earlier.
what's the difference between grep and grep? I don't remember.
ngrep?
Yeah.
I've never used ngrep. The difference between grep and egrep is that egrep is just grep-e. They're literally equivalent. Egrep is just grep, but it calls with -E by default. Yeah, the colored output basically persists in the pipes, which means that there are actually color commands in there to change the color that the terminal knows how to deal with, but you're probably not putting that in you're probably not having your other programs handle that. So it's a pain to work with piping. So RapGadget tends to be easier to deal with, honestly.
You should submit a pull request to black to not add color.
I should actually see Hacktoberfest. I could actually get that shirt.
Dips.
So there's literally what company does that again?
It's DigitalOcean.
DigitalOcean. They have a thing called Hacktoberfest, and you just send 3 pull requests to open source projects on GitHub, get a shirt, which I really should do. I still have time.
I think Josh was saying he's still waiting on his from last year, though.
Oh. But yeah.
There is a free t-shirt.
So I have, admittedly, I'm trying to stay pretty basic here. I have written some much cooler exploits where what I had to do was I put executable stuff into a buffer, and then I put a ROP chain into another buffer, and I overflowed a vtable pointer on the heap. So basically in C++, if you have virtual functions or functions that are different for different implementations of an object, there's a data structure called a vtable, which is just a pointer to all those functions. It's just a list, it's just an array of pointers to those functions. So if you overwrite one of those and that calls a function that's in the vtable, then congrats, you just ran whatever you changed it to point to. And there's no stack cookies on the heap. As long as nothing tries to change the heap and has a chance to catch in between, then you're good. Actually, the stage fright exploit, if you look at the Project Zero blog post Stage Frightened, they actually take advantage of that. They set up the heap so that they can overflow into a vtable pointer, and then that pointer gets called immediately after, before the function even returns. So they're able to corrupt that, and then From there, you can execute a stack pivot, and what I did was I pivoted to, I made the stack where I wrote my wrap chain in, and then that wrap chain called mprotect made my buffer with the normal code executable and ran it. So you can you can get much more complex chain stuff together. And then you get to end up sorting through big lists of this and seeing what looks useful to you, which is really fun with bigger programs. That's why I recommend RapGadget, because I grep hard. Yeah.
So with Wrapper, is there no way to make ingrep, like grep work on that?
It's not worth it.
No,
It's not worth it.
yeah?
I recommend RapGadget because of it. If you're purely doing interactive, looking at it, it's okay. It's colorful, it's nice, but if you can deal without syntax highlighting, RapGadget is better. All right. Anything else?
Use --no color to disable the colored output.
There we go. Fair enough. Feel free. I don't want to type that. I mean, you could alias that. You could alias. You know what? Let's. We're just going to echo. Yeah, basically. Is it no dash color or just one word like that? I have a tilde dot slash. I should have a tilde dot aliases file. It's not auto-completing any of that. Oh well. Oh, that's why. There we go. So that will get loaded next time I run my shell. Thank you. All right. Any other questions, comments? People get anything out of this? Just out of curiosity? Was this helpful? Awesome. So hopefully I've at least introduced enough terminology that you can look up better resources. And I also did go ahead and at the end of this presentation, which I'll put a link to this on Slack, I went ahead and put a couple resources down. So if you use Pwn tools, in PwnLab there's a RAP module, which can search for gadgets in a binary. RapGadget and Wrapper, Radari 2. Steep enough, fairly steep learning curve, but very powerful framework. And honestly, once you get used to it, it's easy. It's not easier to use than IDA free, but it can do so much more. So at least in the free version. And then a couple challenges. I've linked to those RAP challenges that I did the first 2 of for you guys. So see if you can recreate that and then work on the other ones. Over the Wire has really good war games you should practice, and Microcorruption is just a really good website for learning basic binary exploitation stuff too.
And another one that he left out, hackthebox.eu is another really good challenge site.
Does that have a lot of binary stuff?
It
does not.
Does on the challenges. It doesn't on the machine stuff.
Okay.
Until you get to the much harder to exploit.
Okay,
You have
so
ones where you got the right buffer overflows, but those are the higher end ones.
okay, so Clayton just mentioned hackthebox.eu. So yeah, because I mean this doesn't pick you up. So Clayton mentioned hackthebox.eu, which is which does apparently have some buffer overflow stuff for the higher level challenges, and is also, I hear, a really good place to practice for like OSCP, if you're interested in getting that, or just doing general pen testing stuff. Huh? I know. Is that why you keep on laughing?
Clay's so ridiculous.
All right.